Then we're ready to start this second chapter of TCP-IP architecture, and here we will discuss the network layer. Just need to get the focus. The main protocol in TCP-IP and in the internet is the IP protocol, the internet protocol, that we will discuss now, and in particular, its two versions, 4 and 6. IP is very simple. It's based on two principles, that's what we'll see, at least as long as we have point-to-point communication. We will discuss a bit later multicast communication, which is very specific. The first principle is this one. Every interface is, for example, the Ethernet or Wi-Fi interface of this device, has an IP address. We've discussed the addresses last week. And in principle, the address reflects which network the system belongs to. We've also discussed this last week. Second, every packet contains the IP address of the destination. That seems obvious today, but that was really the main fundamental invention of the internet, which, like I've discussed last week, was in fact invented a bit before by Louis Pouzin in the Cyclades network 1 year before. But that is really the main trick that makes everything simple today. Second, every system has a forwarding table and performs longest prefix match on destination address. In some sense, that's the algorithm that describes how forwarding works in the internet. I'm illustrating this on this very schematic slide here. Here I'm showing three end systems, Lisa, Bart, and Homer, connected to a network that has four routers. A router is an intermediate system, a middle box, of the IP layer. So its job is to forward the packets to the correct destination. Every router has a routing table. For example, in router R1, we have here this view. Again, this is a very simplified view. In a few more minutes, we will see how it really looks like in real systems. The forwarding table simply says for any pattern that represents a group of destination, what is the output? For example, capital B dot star means any destination address that starts with capital B should be forwarded to output number 2 here. What is capital B? Well, when it's IPv6 addresses, for example, it is a prefix. So capital B is anything, this block here, the black digits here, that would be capital B. And so on. So the four routers must have the routing tables. That's one of the principles of IP. For IP to work, you must have a routing table. And the routing table doesn't come for free. You must learn it through some mechanism. The major mechanism for routers to learn the routing tables is through a routing protocol. That will be the topic of Lab 4 and Lab 6. There are many routing protocols. We will see 2 of them that are widely deployed in the internet. So that's a different story. For right now, let's assume that the routing tables exist and are written. You can also write directly the routing tables into the routers. We will do that in the lab to get started. That's manual configuration. And then what happens? If A has a packet to send to B here, then the packet goes to router R1. R1 analyzes, in principle, only the destination address. I say in principle, that's the IP principle number 1. In reality, routers in the internet do more than that for security reasons. They do their job of finding where to go, then they do a number of other security checks. For example, they might check the source address to see whether this is an address that's on a blacklist or not. But right now, if we ignore those security checks, the only thing that it will do, it will go to the routing table and try to do a pattern matching with the destination address, B capital D H2. For example, B capital D would be this, H2 would mean 64 more bits that would come after that, and we'll look in the table for a match. This table is very short, it has only 2 lines, there's only one match, it will therefore forward the packet to port number 2. At router R2, the same thing is done, but now there are two matches. There are two lines in the routing table that match this here. So which one should you choose? Then the theory says you should always choose the most specific one, the longest prefix match. So here there are two matches, B, which is less specific than B.D. So you take B.D and you forward the packet to number 2 here. If in contrast, A sends a packet to C, to host number C here, the destination address that will be B.C, here in router R2, there's only one match. It does not match the second line because it's not B.D. It matches a third one, so there is only one line here that matches here. So that's the principle, I'll say the first and most important principle of the internet. Why do we have this? Well, it helps us do some aggregation. In some sense here, we say we can interpret what router R2's routing table says as follows. We say, by default, anything that is in B, you go to number 3. Except if you have B.D, you go to number 2 here. So we can have generalizations in the routing tables, and this is what is essential to compress the routing tables. Here my routing tables are very short, but assume this router is a router of a top-level internet service provider like AT&T or Sprint, etc. So companies that have routers everywhere in the world. So those companies must have a routing table for all possible networks in the world, which for IPv4 is 500,000. But if you can compress a bit by having rules like this, this will help a lot. So that's the first principle. There's another second principle, which says that inside a LAN, inside a local area network, you should not use routers. So if W communicates with P, then W should not send the packet to the router that would then forward it to P. It should send it directly to P here. That seems obvious, but that is reminiscent of the fact that IP has its roots in an interconnection mechanisms of local area networks. Remember, in the 80s, most networks were simply local area networks. Then IP came as an invention that took a long time. In fact, IP was invented in 1974, but it became popular only in 1991 or 1992. So it took 15 years for networks to converge to TCP-IP, and the main landscape was essentially local area networks. And if for some reason you need to interconnect them, then you need routers. But if W talks to P directly, don't use a router here. This is why we need subnet masks that we have seen last week. When W sends a packet to P, it needs to know whether P is in the same subnet or not. If P is in the same subnet, it will send to P. But if it sends to B, which is not in the same subnet, then W needs to send to R. So from the viewpoint of W, the next hop is P or R, depending on the destination address and depending whether the destination address is in the same subnet or not. This is why IP systems must know what is their subnet ID in order to recognize whether other addresses are in the same subnet or not. And we have seen that for that we use subnet masks. So, quick question. I mentioned that W sends to P. If we do a Wireshark exercise here at this point, which IP address will we see in the destination address field? Vote fermé. Résultat visible. Okay. So let's poll again. I close the poll in 5 seconds. And as you can guess, the The destination address is P. In fact, the only thing that we could worry is there an IP destination address? Do we need an IP destination address if we are talking to somebody that's in the same lab? The answer is twofold. Yes, because we use TCP-IP. So it's like a tautology. We use TCP-IP, therefore we can communicate only using TCP or UDP, which require IP, so we must have IP packets. So even if W talks to the printer directly, and you have no router, for example, you're in the field or at home, you take a computer and the printer out of the box, you want to send a document to the printer, they will need IP addresses, right? Which may be a problem if you have not configured a subnet and all that stuff into your machines. What will you do? We will see that there are auto configurations that are possible for those cases. It is in theory possible for W to communicate with P without using TCP-IP. This is called legacy protocols, and in the past there were many of them. There is still a domain where that exists. That is in industrial networking. When you use devices like field bus, when the accelerator of your car communicates with the engine, for example, by sending an electronic signal, it sends a packet that in most modern things will be using TCP/IP, but in some systems don't use TCP/IP. You can use the MAC layer directly to communicate, but this tends to disappear. But it is possible. Some protocols do that. Voilà. We have seen the principles of IP. So every system must have an address. We look at the forwarding table by doing longest prefix match. And inside a subnet, you must send directly to the destination and not to the router. Now let's talk about addresses. As we have seen, there are two formats, IPv4, which is the first steady format, so IP version 1, 2, 3 were experimental. The only one that became really important and is the most important today is IPv4. But as we have discussed last week, since 3 years, I believe, the official standard now is not IPv4, but IPv6. We'll see in the lab that in reality, it's a bit hard sometimes to use IPv6, at least at EPFL. So we will go through both types of addresses, and chances are that over the next decades, we will have a coexistence of IPv4 and IPv6. I've been teaching this course for 20 years. In '96, we did already first labs with IPv6, and I was explaining that in 10 years, we will all move to IPv6, but we are not that fast. IPv4 addresses are 32 bits. I've lost the focus. And they are written, so this is an IPv4 address, 32 bits. We group usually bits by blocks of 4, which gives one hex digit. So this would be one way to write such an address here, but because that was done in the 70s, it was written in this form, using decimal thing, which is a nuisance more than a facility, because finding the bit number 23 in this is less easy than if you use hex digits here, because with hex digits, you have a block of 4 bits that corresponds exactly to 1 digit here. You will need in this lab and in the labs and in this course to be able to convert from one to the other. Many of you know it already. In case you don't, here is a very quick recap. Decimal binary, we can count using any basis. We count in decimal. Why do we use the decimal basis for counting? Right, because most of us have 5 fingers on every hand, so we have 10 in total. That's why we have 10 digits, right? Yes, the number. Computers count with 2 digits, and it's more convenient, in fact, to use 16 numbers. When we want to map exactly from binary here. So mapping is easy in one direction, from binary to hex, because it's just a grouping of by 4. Decimal to hex or binary is more tricky, so typically you use a calculator. But there are things you need to remember. A sequence of 8 bits equal to 1 corresponds to binary 255 and to hexa FF. That's something we will very frequently see. We see it in network masks, for example, when there are ones everywhere. I mentioned a few minutes ago a routing table with a dot star everything. And this is not how it is done in reality. Here is an example of a routing table at this router here. So this router is the router that connects the backbone of EPFL to the router of switch. Switch is the internet service provider that EPFL uses. And the backbone of EPFL is connected, at least on this diagram, at this point here. So the routing table will look something like this. Here's a destination prefix. We use the /24 notation. That means the first, we take this with the first 24 bits. Now this is a group of 3 numbers, 3 decimal numbers, so that's exactly 24 bits. And anything that has this goes to the south interface, that means here. Everything that has this prefix goes also to the south interface. What does it mean here? Well, it means the south and the next hop. So if we look at this line, that means, remember that at EPFL, the 3rd byte is typically used for identifying the subnet. So the 29 subnet is this subnet here, which is directly connected to the backbone. So this router is saying, if I have a packet that goes to this subnet here, I should send it to this router, ED2 minus EL, which is the IP address that corresponds here, 100.2 here. So this is saying this network go to this interface. This other is saying 128.178. That means the rest of EPFL, you go to this router here. So we have a backbone where for some reason one network is directly connected to the backbone and the rest goes via other intermediate routers here. So we find here that thanks to the longest prefix match principle, we can have some aggregation here. We have the EPFL default route. And then we have here 0/0. So that means the empty prefix. 0 means absence of address, and /0 means anyhow we take no bit. And we will frequently find this in routing table. Here it goes to the north interface. What does this mean? Well, an empty prefix matches anything. So for any destination address, there is a match here. So when this router has a packet to send, it will always match this one. If this destination address does not match any of those two, that means if it's not a 128.178 dot something address, the only match is this one. So it means anything except those two will go to this routing decision. This is what we call a default route. That's one way to put a default route in a routing table. There are special addresses. Some of them you must be able to recognize. I mentioned 0, which means absence of address. 0 is an invalid address. If you see an address 0 somewhere, that means there is no address. Sometimes you need a place to put it. For example, when you're looking for an address, but you must still put populate a field, then you put 0 here. There is a special, very convenient address, which is 127.001. In practice, that's the only one that's used. It means this host. So that's the IP address of this machine. So any interface, any machine has this address. And that means if I send a packet to this address, it goes to myself here. That's very convenient. Because for testing, for example, if you're writing a client and a server program, you can first deploy them on your machine by giving the address of the server. This is called the loopback address, and then you can test it before deploying it here. Then we have what is called the private addresses. There are 3 blocks of private address, 10/8. That means to remember, /8 I mean 8 bits, so one number here. So anything that starts with 10 dot something, or anything that starts with 172.16 dot anything, or anything, /12, that means only part of this, or this one, 192.168/16, those 3 blocks are private. Private means, in fact, you can use them freely as you want. They are not allocated to anybody. 128, something is allocated to EPFL. If you do a test, you're not supposed to take those addresses. You're stealing addresses from someone else. So you're not supposed to do that. If you do that, that's hijacking of an address here. So there will be alarm somewhere that will be generated by the security and monitoring mechanisms if you give to yourself this address and you send a packet with this source address, for example. Chances are it won't work anyhow because the routing tables in the internet will send any packet back to EPFL, not to your machine here. But those addresses you can. They are private. That means you can use them for any test purpose. And you can use them in particular for making a private network. So if you do your own network that is not connected to the internet, you can use those addresses as you want, and someone else can do the same and can use the same addresses as you. So those addresses, you could expect that lots of people are using them, not just you. We will see that they are used massively today. In principle, that should be done only for private networks that are not connected to the internet, but we'll see that thanks to NATs, network address translation middle boxes, we're able to connect those to the internet. And in fact, this is a trick that is commonly used with IPv4. IPv4 would not work today without those private addresses here. In the labs or in the examples I give, sometimes I will give an address like 10 dot something, that's a private address. Sometimes I will use addresses that are not those ones, but this is just for illustration purposes. Something similar but different is called the link local address. It's an important thing to understand well. Link local address is also a private address in the sense that, like the others, someone else can use the same as you, but with a big difference here. Those addresses are used only in a LAN. That means a router can never forward a packet to such a destination. Remember, a minute ago we saw when P sends to W, in the same LAN, do we use IP addresses? Well, if you're in the same LAN, you can use your standard IP address, your EPFL address, for example. But if you're constructing a LAN, for example, you're camping in the mountain and you brought your computer and your printer and you want to print something, you can connect the two together. You're not connected to anything else. Then you can use those link local addresses. In fact, some systems, like Windows system, they will try to allocate an address to your machine automatically. If they fail to allocate a good address, like getting it from the EPFL address server, they will allocate those addresses. And we'll see that in IPv6, it's even more systematic. So link local is a synonym for LAN. In fact, link is a synonym for local area network. The MAC layer is sometimes also called the link layer. So they mean the same, exactly. And it means the same as subnet. Subnet, link, MAC, LAN, everything here means exactly the same. Then we have multicast addresses that we will mention a bit later. And one specific multicast, which is the broadcast. You recognize here all bits equal to 1. That means any system, but this is link local. Link local means only in the same subnet. So this is a broadcast. That means this packet goes to all systems that are in the same subnet. Of course, there is no global broadcast. If there would be one, that means you would be able to send one packet and it will go to all machines in the world. Of course, there will be a dream for attackers. If you want to do a denial of service attack, then you would use this. So of course, broadcasts are scoped within a LAN here. When we do Wireshark, we can see some of the fields of the IP packet. So here is the IP packet format. The header, so one line is 32 bits. The header is 20 bytes, which is not short. If you're sending very short packets, for example, on an Internet of Things application, you have there is a penalty to pay for IP, which is the header. Most of the header is the addresses, and because you can imagine with IPv6 it will be longer. And this is the main part of the header. Then another important field is called protocol. Protocol means, in this context, the higher layer protocol that is carried inside the IP packet. What should it be in principle? Well, in principle, it's the transport protocol, because what goes above the IP layer is transport. So it should be TCP or IP. It can be also ICMP, which we will see already in Lab 0. ICMP is the message that is used for managing the IP layer. ICMP means Internet Control Messaging Protocol. It means all the error messages that you send when something goes wrong. For example, you send a packet to the machine and the router is unable to forward it because it's not in the routing table, for example. Then some routers will send an error message saying, I cannot forward this packet, and then they send an error message back to the source. Ping uses ICMP. When we ping a machine, we send an ICMP echo request to the destination, and the destination replies with an ICMP echo reply. So those are the three typical protocols, but there can be also other things. For example, we will see that we can carry an IPv6 packet inside an IPv4 packet. That's called a tunnel. We'll study that in more detail in a few more weeks. So there are much more other protocols, but those are the three main ones that we expect to see most of the time. Okay, a quick question to drill you on what we saw so far. Assume somebody, for some reason, uses a subnet mask, which is this one, right? 255, 255, 254. What mask does it correspond to? If we would say that in clear text, instead of giving a mask, what would it give? I close the poll in a few seconds. And the vast majority says D, which is the correct answer. So that's the kind of intricacies that we have by necessity to manage when we work with IPv4. Here is an application of this. Assume you are designing this network or you have to configure it. So here I have a network. The lines means Ethernet or Wi-Fi connections. I have a router that's connected to some Ethernet here, that's connected to an Ethernet switch here, and I'll have also a host that's connected to this Ethernet switch here. What is a valid choice for the address of this host here? Assuming the other configurations are correct. So assume this is correct. I want to stay with that. I want to give something that's compatible with what is written here. I'll close the poll in a few seconds. We have a bimodal set of answers with a peak at C, but also another peak at A. And the correct answer is C, both A and B. let's see why. So first, the first trick is to see that the host H must be in the same subnet as this interface of the router. So this and that are in the same subnet. So they should have the same subnet prefix. The prefix is the first 23 bits of this. So 24.8 have the same 24 bits. So that's a valid answer. A is a valid answer, certainly. But B, if we look at it in more detail, the difference between 8 and 9 is only the last bit. So they differ only by the last bit, which means the first 23 bits here ignore the last bit of this byte. Therefore, the prefix, the subnet prefix, is the same. So both addresses are valid here. Which you can see here. So the difference between 9, which is given here, and 8, which is given here, is only the last bit here. Voila, that's, I would say, the main tricky part with IPv4. Not very difficult, but need to be careful. And that's sometimes a bit mysterious about addresses, but everything is clear when we go to binary representations. So the current version of IP is IPv6. You might wonder why there is not an IPv5. Well, there is an IPv5. It's called STP. It's a protocol that remained experimental and died away. So the next value that had a future is IPv6. Why did we need to change IPv4? The only reason, the major reason, is the address space. The IPv4 address space is 32 bits, which at that time was believed to be large enough. That's 1 billion hosts, but that is too small if you want to give an address to every device in the world. So you need to expand it. There were proposals to expand it to 64, which would have been long enough. Now it's expanded to 128, so 4 times larger address space, which means that we put that to the power 4. Right, so this number is an astronomical number. It's a huge number. Some people say it's the number of atoms in the universe. So it's a truly astronomical number. So there will probably never be a need for changing that. So IPv6 is probably the final version of the Internet protocol, at least from the addressing viewpoint. Of course, when people moved from IPv4 to IPv6, this move was done by human beings. So as soon as you change some things, human beings say, yeah, but there's millions of things we would like to improve. So IPv6 has a number of details that are different from IPv4, but this is not fundamental. It's just because if you do it 20 years later, you want to do it a bit different. Hopefully better, sometimes not always better, but certainly different. But the first take-home message is, because of those changes, an IPv6 packet is incompatible with an IPv4 packet. So if I have a system that speaks only IPv4 and another one that speaks only IPv6, they cannot communicate. You cannot send an IPv6 packet to an IPv4 machine. This machine will not decode it, will not be able to receive it. And similarly, if you send an IPv4 packet to an IPv6 machine, it will not decode it. In the converse, it's a bit weird. You could say, why did they not make IPv6 backwards compatible? After all, when you have a new version of the operating system, you would hope that a program that was designed for the old version of the operating system would continue to work in the new version. There are historical examples. Apple is good at doing that. They changed the version of the operating system, macOS, and at some changes when they moved to Intel processors, the old version, any software you had for the old OS did not work on the new OS. So that's always a decision. It could have been made compatible, but the decision was not to make it compatible. Making things compatible looks nice on the surface because it means the transition is easy. But most of the time it makes things very complicated. That means you need to continue supporting things that were done decades ago, even though quasi nobody uses them today, but you still need to be able to support them. So that makes the system very complicated. So software people tend to say, I don't want my system to be compatible. But sometimes the marketing departments of companies will say, but you must make it compatible. Here it is not. So routers and hosts must handle both separately. Of course, there are links between the two. In particular, we'll see that TCP is the same, but the networking layer is different. So a system that has both is called a dual stack host. Stack means the protocol stack means the whole set of layers, which is a bit incorrect. We should say dual network system, but they're called dual stack. Depending on the system, systems like Windows, for example, really treat IPv4 and IPv6 as two completely different things. Systems like Linux tend to try to unite them as much as they can. And we'll talk more about that a bit later. So most machines that we have today are dual stack. I mean, if you want an IPv4 only machine, probably it's a very, very old software, Windows 2, for example, did not even have IP. So Windows 3 had IPv4 only, but those are really exotic cases here. But even if you have a dual stack machine, it is not guaranteed that you have an IPv4 and an IPv6 network access. In many places, like here at EPFL, we have practically only IPv4. On the Wi-Fi of EPFL, we have only IPv4. In other places of the world, you have only IPv6. Remember, the motivation for IPv6 is the depletion of addresses. There's not enough addresses to give to everybody. So some cellular operators start having services that are only on IPv6. So you may be in one or either case. You can have only one or only the other. We will see how to make things compatible in this case here. Here is how a routing table looks in the case of IPv6. So IPv6 addresses are much longer. They are written using this format that I will explain a bit later. A main difference here is that typically when you use next hop routing table, the next hop is a link local address, which was not the case in IPv4. Here is the IPv4 routing table of this router here. The next hop is a global IP address. In IPv6, link local addresses are used systematically. They are exceptional in IPv4. In IPv4, you use them when you're stuck camping in the mountain and you have no internet and you still need an address, so you give this link local addresses. In IPv6, every system always uses link local addresses. We'll talk about that in a few more minutes here. And in particular, that means that the address being link local does not specify exactly where it is. So in this here, if I give the IP address here, the IP address means it must be on this interface, because by analyzing the subnet prefix, I know on which interface it is. If I use a link local address, it's not possible. So some systems will, in addition, need to give the interface number in the address. So if you see a %2 at the end of an IP address, that means two things. First, this address is link local. Second, the % is the interface number. You will see in the lab, we'll see that machines have typically interface numbers that can have any kind of names. In Linux, they're called ETH0, ETH2, etc., even if they are not internet. We need to decipher IPv6 address, which is simpler than IPv4 addresses because we use X digits. So they are 128-bit long, which is long. So it looks more like a password, a secret password, than an address. So in practice, an IPv6 address, there's little chance that you will know it by heart. So it looks like more a random sequence of digits here. But there is some interesting things. Here's, for example, an IPv6 address of EPFL. EPFL has IPv6 on the wired Ethernet, on the Ethernet part of the network. And if you ask explicitly, you obtain one address. So I asked explicitly for my office, and I have this address here. And if you analyze this address, you will see several things. You will see it starts by 2001 620, 618, and we see here that the 2001-620 is in fact a prefix that is allocated to our service provider switch. So that's an example of an IP address that we have obtained from a service provider, and the from the service provider is visible in the address here. So 618 identifies EPFL. Why is that interesting? Well, imagine you are a backbone router of the internet. You see a packet that has destination address EPFL. If it's for IPv6, you don't need a routing table entry for EPFL, because if you're in the backbone of the internet, you will first send the packet to switch. Switch internet is not directly connected to the backbone of the internet, to what is called the tier 3 service providers, the highest level service providers. So we go via switch. So all you need is a routing table for switch 2001-620. For IPv4, it is not possible, because the different IP addresses of the customers of switch, they have nothing in common. So you cannot aggregate them. They're not derived from the same block. And this is because the space of IPv4 is small. So one reason given for making the space, the address larger, is not enough addresses. But there's another reason, is being able to structure the address. If we structure the address, we have prefixes and sub prefixes, then we're able to aggregate more. And the result is today, a routing table for IPv4 and the backbone of the internet is 500,000 entries for IPv4, because we're not able to aggregate a lot. For example, in all backbone routers, there is one block for EPFL and one block for ETH, even though they all go to the same service providers, but those two blocks cannot be aggregated together. For IPv6, there's less than 100,000 blocks. So we've divided by 5 or 6 the number of blocks. Why is that important? Well, a router, remember the slide we saw at the beginning of this hour, a router looks up its table for every packet. That's the principle of IP. So that's a real-time function that needs to be done for every packet. If you need to look up a table that's 500,000 entry for every packet, that needs considerable hardware sophistication. So that's expensive. So there's hardware assistance in IP routers just to speed up the time of looking up on the table. If you can simplify that by design, then it's better, which is what IPv6 does. Before we dive into the specific IPv6 addresses, we need to discuss rules about writing IPv6 addresses. In the computer, they are a string of 128 bits, but we'll need to write them for humans. So when we write them by pieces of 16 bits. For example, here, separated by colon. I call it a piece. This is not the general terminology. I don't think there is a general terminology. If you look up Wikipedia, they call it a block, but the block of addresses is used in the context of routing protocol for a set of addresses that are allocated to specific domains or specific needs. So I don't like this word blocks, and I use the word piece. I think the most correct term is hextet, which means a word of 16 bits. A byte is 8 bits. Hextet, a double byte, is 16 bits here. So for example, here's an address. To make it readable, we separate the blocks. And then, if the address has many zeros, we can compress it by applying 2 rules. Leading zeros in one piece are omitted. We see that here. For example, I have 0620. And then we display as 620, which is what I displayed in the previous slide. So in fact, this was a block. When I say 620, it's a block of 4 hex digits, not 3. There is a hidden 0. And then if there is a large number of zeros that are contiguous, you can omit them by doing this double colon sign. Of course, this can exist only once in an address, because if it exists 2 times, we don't know how many zeros there is. So this address here can be decompressed to that here. So that is very frequently used to make addresses shorter, look shorter. We have seen examples of addresses. The so-called global unicast address, those are the standard addresses. Those are IP addresses. Unicast, that means they are not multicast. We have seen already multicast addresses and broadcast. They are the addresses of only one machine. And they are global, that means they are the normal addresses that are visible in the public internet. The blocks that are allocated today are the blocks that start with 2000 and 3000. I say 2000 like everybody does, but this is incorrect. 2 followed by 3 zeros is not 2000, right? This would be 2000 if this would be decimal digits, but those are hex digits. So it's not 2000, it's much, much more than 2000. But we read it as 2000 here. So the block 200/3, that means the first 3 bits of this, which means in clear text, anything that starts with 2 or 3, they are the valid global unicast addresses today in the internet. And all addresses we have seen fall in this block. And we will do a break now and continue discussing the addresses after the break. So we break until 1:15.